move now to the second presenter, Dr. Rachel Lowe from the London School of Hygiene and Tropical Medicine. We alluded to some of the, when people talk about the explosive, how to put it, march of dengue from the 1970s to now, from a handful of countries to over 100 odd countries now presenting, it's really been underpinned by the redistribution of the vector, Aedes aegypti or Aedes albopictus, establishing themselves outside of tropical, kind of the traditional homes, as it were, the kind of tropical envelopes, the tropical climates. And in part reason for that, in part has been the effect of climate change on that. And it's doesn't seem to be abating at any point. We've had cases all the way into the European mainland the last 12, 18 months at higher altitudes such as Nepal. We've charted dengue outbreaks in newer. Yesterday we heard from the Ethiopian CDC about a new outbreak that happened in Ethiopia, and in their opinion how it's there to stay and it can only really get worse. So this whole concept of climate change, how it's feeding into vector distribution, also impacts to migration, and all of it is a fascinating and very, very important consideration for dengue moving forward. And so we're very, very honored and very, very happy to have Dr. Rachel Lowe talk about this. And so I think I'll pass the floor over to you, Rachel, in terms of hydrometeorological hazards and dengue early warning system. So over to you, Rachel. Thank you.
Thanks very much, Kamran. Thanks for the opportunity to present today. So I'm Rachel Lowe. I'm an associate professor at the London School of Hygiene and Tropical Medicine. I lead the Planetary Health and Infectious Disease Group. And we're very much interested in how we can use climate information to strengthen decision support systems for dengue and other climate sensitive diseases. We're particularly interested in how we can move from global observations of the Earth to develop tailored decision support systems at the local scale. And in order to do that, we need to be able to formulate models and data pipelines to be able to incorporate Earth observations and epidemiological information together into models and co-develop what we call climate services for health to try and transform this climate information into something that can be useful and actionable on the ground. So the ultimate goal is to shift from a surveillance framework where we're just relying on cases being reported before we can take any action to a predictive framework. We do that by trying to understand the links between climate and environmental factors on diseases like dengue. And where we can, we extend this lead time even further by using forecasts of the climate, but at the same time taking into consideration the additional uncertainty that's introduced into your model by using forecast climate. So this map here is just showing us the correlation between the sea surface temperatures in the Pacific and rainfall. And this is showing us the kind of patterns we see when we have a warming of the sea surface temperature, which is called El Nino, and how that impacts rainfall levels across the globe. So we can see there's a positive correlation between El Nino events and rainfall in the coastal area of Ecuador, which is a place where we've been working. And in 2016, following one of the largest El Nino events on record, the city of Machala in southern coastal Ecuador experienced one of the worst floods since the El Nino event that happened in 1998. And this was also followed by an earlier dengue season than expected, given these sort of conducive conditions for a dengue outbreak with the flooding and the warm temperatures. And we'd built a dengue prediction model using the historical data in the city. And for the 2016 season, we produced a probabilistic dengue forecast using an ensemble of climate forecast for precipitation and temperature, which allowed us to predict an early peak in dengue 3 months earlier than would have been expected, just relying on the endemic channel alone. And so this was partly possible because seasonal climate forecasts tend to be more reliable during El Nino events. And this was a nice demonstration of how climate information could be linked to epidemiological data to produce a early warning system in advance. We've also been working on a UK Space Agency funded project to develop a satellite-based dengue forecasting system in Vietnam. So our team at the London School of Hygiene and Tropical Medicine has been developing the dengue modelling work of this. It's a project in collaboration with HR Wallingford and the Met Office, the WHO and UNDP in Vietnam. And this is an article that was published a couple of months ago, led by Felipe Colon, developing a probabilistic model to incorporate different streams of climate information and climate forecasts to predict the risk of dengue from 1 to 6 months in advance. So we validated our system, looking at different forecast horizons from 1 to 6 months in advance across the seasons and over space. We could identify that our model was skillful between 1 and 3 months in advance. And in particular parts, particular places and seasons, we could see where we had greater skill and there's more scope for developing more localized district level forecasts in those areas. And this work has been developed into an operational prototype of a climate-driven dengue early warning system. This platform has been developed and is shared with our health partners in Vietnam. So every month they're able to see the forecasts produced by our model and the probability of exceeding different epidemic thresholds depending on where you are and the particular stakeholders. I've also been working with colleagues on trying to develop decision support systems for arboviruses in the Caribbean. So the Caribbean, like many parts of Latin America, has been facing the crisis of co-occurring epidemics of dengue, chikungunya and Zika. And it was observed by our partners, particularly in Barbados, there was an increasing incidence of dengue outbreaks following drought events. So we wanted to explore this a bit more, and we explored the historical dengue data along with drought indicators and other meteorological variables, and found an interesting nonlinear and delayed impact of droughts and extreme rainfall on dengue. And we reported these model findings in an article in PLOS Medicine. We've also published stakeholder engagement studies detailing the findings from engaging with different climate and health partners in the region, trying to identify what actually is important and what is needed in terms of climate sensitive disease early warning systems. We've also been working with our partners at the Caribbean Institute for Meteorology and Hydrology and have published in the Bulletin of the World Meteorological Organization. So this is showing the findings of our model combining a distributed lag nonlinear model with our Bayesian probabilistic model framework. And we found both an increased risk of dengue immediately following exceptionally wet conditions, but also around 3 to 5 months following particularly dry conditions. And this relationship has been very interesting, and we've also found something similar in Brazil, which I'll show later on. So this pattern has been recognized and incorporated into the Caribbean Health Climatic Bulletin. Last year, there was a region-wide drought in the Caribbean, and then there was a forecast for exceptionally wet conditions. So a warning went out to dengue control teams, particularly in the Eastern Caribbean, to be aware of the potential for needing to eliminate mosquito breeding sites in water storage containers, which have been used to mitigate the impacts of droughts. So we're now developing our model framework, and we're trying to really simplify this down so it could be used in a operational and sustainable way. So we're now trying to select the best combination of lags from using minimum temperature, short and long lead drought indicators, so that we can optimize the inputs, the climate inputs into our decision support system to make it easy and user-friendly for the meteorological services to be able to produce probabilistic dengue forecasts on a routine basis. So in this particular model selection exercise, we've found that using a minimum temperature with a 5-month lag, the standardized precipitation index with a 4-month lag and with a 1-month lag gives you that best combination and allows you to capture some of those things we observed with our more complex model. So we see, particularly if we have very warm conditions, you do see the greatest risk when you have particularly dry conditions followed by particularly wet conditions. So this simplified model allows us to capture that relationship. And with this framework, we've been able to produce probabilistic forecast with a 3-month lead, which we've been validating using historical data. So this heat map on the left shows us the probability of an outbreak compared to an actual observed outbreak from June 1999 through to May 2019. So we hope to see the crosses coinciding with more orange to red areas, showing that there was some probability of observing an outbreak. And we're also using receiver operating characteristic diagnostics, and we found that our model has an overall area under the curve of 73%, which means it's significantly better than randomly guessing, which would give us an area under the curve of 50%. And we've been comparing this to a baseline model based on seasonal averages alone and seen that our framework is more skillful than relying on current practice. So this is just a framework of how this would work in practice. If we wanted to produce a dengue forecast valid for the month of August, then we would need to combine observed data from weather stations across the island of Barbados. So they would be observed up to April and combined and input into the model in May. And then we would also take the observed precipitation and combine that with forecast, the forecast of that standardized precipitation index to produce a forecast valid for the month of July, which is the month previous to the dengue month we're interested in. So this is a framework combining observed and forecast climate indicators to give us a 3-month lead probabilistic dengue forecast. So what would this mean in terms of scenarios? So if we were to have a hot and dry season followed by particularly wet conditions, then our model would predict a high risk of a dengue outbreak. Whereas if we had a cool and dry season and those dry conditions continued, our model would predict a low risk of a dengue outbreak. And we've developed an interactive app which allows users to produce forecasts and different scenarios based on a combination of different climate conditions. Recently, last week, in fact, we gave a training webinar to our partners in Barbados. This was part of a consultancy we've had with the Red Cross Climate Change Centre and sponsored by the French Red Cross, where we've been working on developing this impact-based forecast methodology. And we shared with our partners in the region and a combination of climate and health stakeholders, technicians and data scientists, how to actually develop this methodology, how to convert it into an online app. And with our partners in the meteorological services, they showed us a demonstration of how this kind of model could be incorporated into their suite of climate services on their website. This is an example of what the framework would look like in practice. So this is a mock-up by the Barbados Meteorological Services. So this is translating our framework into a impact-based forecasting framework. So we're currently working with our with the Ministry of Health and Wellness in Barbados to design the kind of messaging that would go with the different level of certainty we have and the different risk levels of a dengue outbreak. I'm now going to talk to you a bit about our work in Brazil, which started several years ago when we developed a prototype dengue early warning system ahead of the World Cup in Brazil, which gave us an opportunity for the first time to put our modelling framework into practice, and we were then able to evaluate how well our model did after the event. And we've recently been developing this framework and trying to bring in this idea of the sort of interaction and delayed effects of hydrometeorological hazards. And we're moving now from a small island developing state setting to a very diverse landscape with many different rural urban settings. And we wanted to understand how that was interacting with the underlying landscape. And this is particularly important because over the last 2 decades, we've seen a complete change in the dengue epidemiology and an expansion of the dengue transmission zone. This is some preliminary work by Sophie Lee as part of her PhD, looking at how dengue is expanding both into these more remote areas in the Amazon and also shifting down into the south, and trying to understand if this is driven by warming temperatures, but also by increased mobility and connectivity, particularly into the remote areas in the Amazon. So I've been trying to apply the framework I presented for Barbados to try and understand how drought might be impacting the occurrence of dengue outbreaks and other Aedes-borne diseases, and how this interacts with the complex urban landscape and the inadequate infrastructure, which often leads to people being subject to water shortages and being forced to store water. So what we did was we combined the level of urbanization across Brazil with the reported number of water shortages. We combined this with the Palmer Drought Severity Index to try and understand this pattern between extreme drought, extremely wet conditions, and more urban and more rural areas. And we found, surprisingly, a very similar pattern to the one we found in Barbados. And we found that the drought effect was particularly exacerbated in urban areas. And we think this is due to particularly people being forced to store water in those areas where the water system fails when there's drought, and the urban environment providing that perfect environment to be able to sustain mosquito transmission during drought periods. We also observed that the impact of extremely wet conditions was slightly more immediate and exaggerated in rural areas. So when and where might this kind of early warning system be useful? Well, particularly, this is showing us the link between the El Nino Southern Oscillation and the drought indicator on the left and temperatures on the right. And we can see, particularly when we have El Nino events, we seem to have a high correlation with drought across sort of southeast through to the north of Brazil, and also particularly warming in the Amazon. So there's a potential to be able to develop this into a framework similar to what we are doing in Barbados. This here is just a schematic of how it may be necessary to design landscape-specific forecasting scenarios. So particularly being aware of extreme drought events and forecasts in the urban areas and extremely wet conditions in the rural areas. And this is something which is a work in progress at the moment. So thank you very much for your attention, and I'd welcome any questions.